Hi everyone, I'm Ratish Pandey from Educational Series. Today we'll start a new topic, light, reflection and refraction as a part of Aryabhatta series. So let's start. Before moving on the video, please like, share and subscribe my channel and also click the bell icon segment below to get regular update of my videos. So here is the mind map of the whole chapter. We'll study this. I have divided this chapter into two videos. In today's lesson, we'll do reflection, types of mirrors, plane mirrors, spherical mirrors, types of spherical mirrors such as concave and convex, components of a spherical mirror, and rule of image formation and ray diagram of spherical mirrors. So let's start. So first of all, what is reflection? So when light falls on a substance and that substance has the property to reflect it, that is called reflection when a light is bounced off of a surface and reaches our eyes, which gives us a reflection. Such as you can see, the light falls in the water and we can see a beautiful reflection of the mountains above. So now let's see the laws of reflection. Laws of reflection are that the angle of incidence is equal to the angle of reflection, and incident ray, normal, and the reflected ray lie in the same plane. So reflection occurs in mirrors, as we all have in a house. We use mainly reflection which we use in our daily lives. It happens in mirrors. So they are plane mirrors which are in our homes, which we use, such as this one, and spherical mirrors such as these, using dish antennas and for example, the car side windows, side mirrors. So there are two types of spherical mirrors or circular mirrors, concave mirror and convex mirror. Now let's see the components of concave mirror or convex mirror, or they are both are the same, spherical mirror on the board. So let's see spherical mirrors. So a spherical mirror is basically a part of a huge sphere. Glass, it's made up of glass. The spherical mirror is basically cut off from the sphere, and which is a part of a sphere. Now we will see about the parts or the components of a spherical mirror. Before going to the components, let's see the types of spherical mirrors. So here are the two types of mirrors, concave and convex. So in a concave mirror, the concave mirror is bent inwards and the convex mirror is bent outwards. Now we understood that this mirror was a part of a sphere glass. Now when we took out this piece from a spherical glass, is it a mirror or it's not normal glass? It's still the same normal glass, such as of this lens. If I take it out, will it become a mirror? No, it's not simply glass. Now as we see a reflection, we use mirrors to see our reflection. Then as we learned about reflection, there should be something that reflects most of the light. Now we cannot take water inside a mirror. It's not usually, it's not what we see in a mirror. So now we'll see that silver. Now silver is basically should be used because it reflects 98% of light that falls on it. Now suppose think that our mirrors has silver coating at the back of them. Now there are many millions of people who have mirrors in their homes. Now around half of the world have mirrors in the home. So will they be able to afford silver coating on the other side of the mirrors? No. That's why we use silver paint, which is easily available and cheap. That's used to paint the outer side or the back side of the mirrors, of any mirror, which helps us see our reflection. Now these concave and convex. So in a concave mirror, it's polished on the back side, on the outward side, while in a convex mirror, it's polished inside. Such an example of convex and concave mirrors is spoon. Now if you see it from here, it's bent and you can see a reflection is somewhat like a concave mirror, while the another part of it is bent outwards and shows a reflection. It's an example of convex mirror. Here you can see a reflection in the both the sides. So it's an example of concave and convex mirrors. Now let's see the components of a spherical mirror. Now let's see the components of a spherical mirror. So the first component of a spherical mirror is center of curvature. Now as we saw that a concave or convex mirror is a part of a sphere, then that sphere would have a center. That center is known as the center of curvature. The center in a concave mirror, or I'll show you the example like here. In the concave mirror, the center of curvature is at the front in the center, and in the convex mirror it is at the back side. You can see it better here. It is because now the reflective surface is here, then this portion is known as the back side of a convex mirror, the opposite side where we have put polished it. So at the center of curvature is behind of a convex mirror. Concave mirror, the center of curvature is in the front, while in a convex mirror the center of curvature is at the back, while the polished area is here. Now let's see the second part, which is known as aperture. So in a mirror, the whole reflective area, means the area you can see reflects all the, because now if this area on a concave mirror is polished, then area from here to here till we can see a reflection is known as aperture, or the surface area of a mirror where we can see a reflection. The third component is known as the pole. Now the center of a aperture is known as pole. It is in front, is exactly in front of center of curvature. The fourth is radius. Radius is the radius of curvature, or the radius is the distance between the, now see, it's a point to be noticed that radius is the distance between the center of curvature and the pole. While the next component, principal axis, is the line, imaginary line that goes on, that passes through the center of curvature and the pole. Now radius is the distance between the center of curvature and pole, while the principal axis is the line that grows on, cuts off through the center of curvature and the pole. And this now this suppose the half at the exact center of the center of curvature and a pole is known as focus. So it's exactly in the center of curvature and pole. Now the distance between the focus and the pole is known as focal length. It's not a part of a mirror, but for it will be used in numericals, which you will do in the book, so that it comes useful at the distance between. It also comes in CBSE 1 mark question. What's that called? The distance between focus and pole, or what is focal length? So the answer will be the distance between the focus and the pole of a spherical mirror or any mirror is known as focal length. Now we are done with the parts of a spherical mirror, and the rest, if any part is missed, we'll see in the PPT. Now let's revise what we have learned. So the pole is the center of entire reflecting surface of a mirror. It lies on the surface of the mirror at the center of the surface of the mirror, which I have already told you. And the pole is usually represented by the letter P. Center of curvature, the reflecting surface of a spherical mirror forms a part of the sphere. The sphere center is known as the center of curvature, as I have already told you above. It's represented by letter C. Center of curvature is not a part of the mirror. It lies on the outside its reflecting mirror. It's not a physical part of a mirror, but it's used for making ray diagrams and how rays go when reflected by a spherical mirror. Center of curvature of a concave mirror lies in front of it, while the center of curvature of a convex mirror lies behind it. Radius of curvature. Radius of the sphere which the reflecting surface of a spherical mirror forms a part. As I have already told you, here I will make this here a circle. So now from the center of curvature, which is approx here, the distance from the here to the circumference at any point at the circumference is radius. So suppose if this is a mirror, then the distance from the center of curvature to the pole is known as radius of curvature. It is represented by letter R. Principal axis, a straight line passing through the pole and the center of curvature of a spherical mirror. The principal axis is it's too fast. Principal axis is normal to the mirror. It's behaving bad. Principal focus, ray parallel to the principal axis fall on a This is the definition of focus, that rays parallel to the principal axis fall on a concave mirror, meet and intersect at the point known as principal axis. The point is called the principal focus of a concave mirror, or we will see this in the simulation after we cover all the parts. The reflected ray appear to come at a point on the principal axis when the rays are parallel, on the principal axis fall on the convex mirror. That point is called principal focus of convex mirror. Now you would have noticed that here is written appear. Means appear, it's not real. We cannot, because in a convex mirror it diverges out all the rays, which we will see in the simulation at the back side of the virtual side of the convex mirror, that forms a point or the focus which is same as the center of curvature behind the reflecting area of convex mirror. Principal focus is represented by letter F. Distance between the pole and the principal focus of a spherical mirror is called the focal length, as I have already told you. It's represented by letter small f. A portion, as we have discussed earlier, the diameter of the reflecting surface of a spherical mirror is called aperture, or the whole reflecting surface. A mirror whose aperture is much smaller than the radius of curvature. Mirrors. So basically, it does nothing. So how to find the focal length is the rule is equals to R is equals to 2F. Means the radius, the focal length is half, because the focus is half of the radius at the center of the radius. So the focal length is half of the radius. Before moving on, please like and subscribe my channel, and don't forget to click the bell icon segment below to get regular updates of my videos. Now this video is naughty. A part of Aryabhatta series where I post some video per week, some interesting videos with high quality concept and using PPTs and a great knowledge which you can get from our videos in the Aryabhatta series. I have made many other series. Please Please check in the playlist in the channel given below. Click the subscribe button and please join to our educational family. Now let's see the simulation. In the simulation, we'll learn more about concave mirrors and convex mirrors and how they focus. How about their focus? So let's start. Is a ray optic simulation. You can see the link here. If you will search in Google ray optic simulation, then you'll get it. Now, so for a spherical mirror, I'll select the option and I'll make this a concave mirror. Now let's see what happened when I beam a single ray on this. You see, this ray is reflected outwards. Now let's see what happens in case of a convex mirror, which is reflected outwards. Now let's see what happens on a concave mirror when we show a lot of infinite number of beams of light parallel to the principal axis. You see, all the light that fall on concave mirror just got converged on a single point. So we here learned that all the rays which are reflected on a concave mirror, all the rays reflected, the concave mirror converges. It's on a single point. All the energy which is given to the concave mirror is converged on a single point, which is known as the focus. Such as now in the case of a concave mirror, when we adjust a concave mirror such in a manner that the sunlight falls on the mirror and falls on a sheet of paper. Now all the sunlight, you know how huge and bright is sun. So now all the energy of the sun falling on that upper sheet or this big surface area, this concave mirror converges on a single point. That point falls. That all the energy falls on the paper. Now, if sun is so huge and all its energy which falls on a concave mirror will be diverged on a single point, that causes the paper to ignite or burn up. We can see the smoke coming out and the paper starts burning because the light of the huge sun or the mighty sun fall on a one point in a paper which ignites it. Now let's see what happens when we throw a beam of light on a convex mirror. Oh, now you see that all these light are diverged out. That's why convex mirror is also known as diverting mirror, which diverts all the light outwards. Now, if all the lights are going outwards, then how will you find the focus? Because focus is where the lights join together. But we have learned about the focus of convex mirror. What should we do now? So here we'll use an extrapolate. Now what is extrapolate? It's extending at the back. That forms, now you see that if these are going in one direction, let's see what if we extend those rays virtually at the back. So here you can see what happened. Magic. We extrapolated those rays and at the back, the virtual side of the mirror on a convex mirror, they converged. And that point we cannot see, but we know or we can imagine that all the points, all the lines converge this single point behind the mirror virtually. So such an amazing magic to see. Now we'll come back to the simulation after some time. Now let's see the image formation by mirrors or standard incident rays. So there are 4 rules of standard incident rays. We will study them one by one. A ray parallel to the principal axis after reflection will pass through the focus. In case of a convex mirror or diverge to pass to the principal focus in a convex mirror. In case of a convex mirror, a ray passing through the principal focus of a concave mirror, which is directed towards the principal focus of a convex mirror, gets will emerge after reflection will emerge parallel to the principal axis. And the third, any ray passing the center of curvature of a concave mirror or directed to pass through the center of curvature of a convex mirror retraces the same path backwards. A ray incident obliquely to the principal axis toward the pole of the mirror on the concave mirror or a convex mirror is reflected obliquely. Basically, it means that if a ray of light falls on a pole, then at the same angle it will reflect back. Now we'll use this standard infinite rays or image formation by mirrors while doing the ray diagrams. Now let's see the ray diagrams. Oh, before moving on, here you can see the how it proves this image proves the light comes and it passes through the focus and becomes parallel, and here in the convex mirror it passes through the focus, it is directed towards the focus and becomes parallel, and here the light from the light comes is parallel to the principal axis, comes passes through the focus, and which is directed right beam in a convex mirror is so here in a wax mirror, here with the line is perpendicular to the principal axis, is directed towards the imaginary focus, and it's it's reflected up, and here any line principal in a concave mirror is perpendicular to the principal axis, passes through the focus, and in the case of a convex mirror, any line principal to the perpendicular to the principal axis goes back in the front of the opposite direction of a imaginary focus. Here same, in a concave mirror, light beam passes through the center of curvature and retraces back, and here the convex ray passes to the imaginary here, and it's directed at the center of curvature and retraces back. And here these both are same, the light comes on a pole and gets reflected back in case of concave and as well as convex mirror. Now let's see the ray diagrams of concave and convex mirrors. Now let's see the ray diagram. First we'll come to ray diagram 1. So the object here is at infinity. So the light rays come parallel to the principal axis. So as we have learned in the standard incident rays, that any line that is parallel to the principal axis when reflected by a concave mirror passes through the focus, or any convex mirror also. So these rays when reflected pass through the focus. So this is the ray diagram first, where the two rays with the object is at infinity. Now this is the ray diagram. So CBSE asks about the image, position of the image, where the image is formed. Image is formed at the focus. Now the next thing it asks, the nature of the image. Now any image in front of the mirror is real and inverted, and because it's front of its and size. Now size is determined by the distance between the principal axis and the last point of the object. Now this or the image of the image. So now the image is just closely glued to the principal axis, so the size will be highly diminished. Actually, highly diminished. So now, is something lacking here? right? So here now, if you are making any ray diagram, most important is just to mention the which ray is it and the arrows. Now this is the incident ray 1 first, and this is the reflected ray 1. Now because the examiner needs to know which ray is which one, so we have to mention. It's very important, or you will not get even 1 marks. How will the examiner know? You know, but the examiner don't know that you know. And this is ray 2 and reflected ray. So it's very important to mention those. Now let's see our favorite ray diagram 2. Now let's see ray diagram 2. So here, now let's see what happens in the ray diagram 2. So again, now the object is between C and infinity beyond C. So now the light rays come and divert as they are perpendicular, parallel to the principal axis. They diverge to the, I'll make it a little bigger. They diverge to the focus. So when we draw one ray which is parallel, as I've already told you these all. And now now another light beam passes to the center of curvature. Center of curvature is here. Passes to the center of curvature. So as we studied earlier, when a light passes to the center of curvature, it retraces the same path. So it retraces the same path. So what are the rays? Incident ray 1, reflected ray 1, and incident ray 1. Incident ray 1, incident ray 2, and the same reflected ray 2. So here now, point to be noticed that earlier in the earlier diagram we saw when the object was at the infinity, the image formed at the focus. Now when the object is at beyond C, means closer between infinity and C, then the image is formed between center of curvature and the focus. This is the ray diagram 3. Now we can see where is the position between C and F. Nature, we all know, real and inverted. And size. Now the size here, it's this big, and the size of the image is smaller. So we'll not say it highly diminished, but we'll say it diminished. Now let's further progress on. See ray diagram 3. So now the object is at the center of curvature. So the light rays is perpendicular to the principal axis and passes through the focus. And now again the light ray, we have learned, if light ray passes through the focus, then it becomes perpendicular. So here sorry, it's a little problem, and it is so the image will be formed here, and as the light beam is going, then it will become perpendicular, parallel. And the image is formed on C. When you will do with scale, then you will get the exact measurements, and you can see that now the size is same of the object and the image. And now let's see let's make the arrows. It's incident ray 1, reflected ray 1, incident ray 2, reflected ray 2. So here at the intersection the image is formed. Now position on C, center of curvature, nature, we know real and inverted, size same as the object. Done. So how you see how easily we are going to the diagrams of concave mirror. After there are 3 more diagrams, then we will see the 2 diagrams of ray diagrams of convex mirror, and we'll get some learning tips. Then we will see these summary of the table form which I have shown you. These all here in the form of table on the PPT. Now let's see ray diagram 4. So here now the object, earlier the object was at C. Now the object is between C and F. Now it will they are rays perpendicular, so it will pass through the focus. I'll make it a little farther. So now this now a light beam as you know passes is here passes through the center. Passes through the center passes to this C. Then it traces back. So it goes, and here these both meet, and they here the image, or if you will draw it with lines, I am drawing it roughly here. So the image will be formed at this place. Now as we measure from principal axis, now the image is so huge. The object is so small and the image is so huge. So first we'll make the arrows. Incident ray 1. Sorry, balloon burst. Reflected ray 1. Incident ray 2. And reflected ray 2. So here, as we saw that the image is so huge, and here it's between infinity and C. The image is formed between infinity and C. The position of the image will be between infinity and C. Nature, we know real and inverted. Size, enlarged, because it's many times bigger than the object, so it's enlarged. This was the ray diagram 4. Now let's see ray diagram 5. So now let's see ray diagram 5. So our object is as infinite as focus. So perpendicular passes to the focus. Now this line goes, here it starts. It's a little, the object is a little bigger. So it retraces the same path, as we know that it retraces the same path back. Oh my god. Now what just happened now? They are not converging at a point. If they are not converge at a point, how will an image be formed? So now, as we saw universe is parallel. It's what believes that parallel lines never meet. So nothing in the world is parallel. Nothing. You may be now thinking that you studied many laws and parallel lines, this, blah, 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 blah. Now, it's not wrong, but approximately these are parallel, so in mathematics it would work. Basically, no lines are parallel. Here, these two parallel lines, we suppose or we think that these two parallel lines go and meet at infinity. So suppose that here is infinity, they go and meet at infinity. Now if this is, we don't approximate for approximation, we are taking it, or wait, they are not meeting. At the infinity they will meet. So if now if the size, if they will meet here, we could take the size here, we could calculate the size. But how will you calculate the size where at infinity? So the size already done will be highly enlarged. Sorry, size done, highly enlarged. So now let's see the arrows. Incident ray 1, reflected ray 1. I have already told you, it's very important to mention those. Incident ray 2 and reflected ray 2. So now the position, infinity, nature, real and inverted because it's still in front, real and inverted. So this is fifth ray diagram. Now let's see sixth ray diagram, which is very peculiar and unique. Now let's see ray diagram 6. So now this ray diagram 6 is the most unpeculiar or unfamiliar in compared to all the other ray diagrams of concave mirror. This is very strange and different of what usually happens in another concave mirror ray diagrams. So now let's see what happens in this. Now the object is between F focus and P pole. So when the light, as we know, when the light ray passes through, which is parallel to the principal axis, sorry for the disturbance, passes through the focus. Now another ray which passes through the, now we know a ray that passes through the center of, a ray that passes through the center of curvature retraces the same path. So now this ray retrace the same path. If you will do with scale, you can have more clarity. I don't have a scale here. Now what you observed here? Now these two rays are going diverging out. Now if they will not meet at a point, then how will the image will be formed? As the image is formed only when two or more light rays converge at a point. Now what will happen? So this in here, now this mirror gives us the image behind the mirror. As you can see, these two rays converge behind the mirror. So what we saw here, I'll do it here. The position behind the mirror. Nature, now because it's behind the mirror, we have learnt virtual and erect. Virtual and erect. Size. Now you can see, as we know the size through the principal axis. Now can you see the image is much bigger than the object, so it is enlarged. So here was the ray diagram of concave mirrors. Now we will do the ray diagram of convex mirrors, and then we will go on to the PPT. So here is ray diagram of convex mirror. There are two ray diagrams of convex mirror. First one is shown below here. So now the object is at infinity and the light rays are falling parallel to the principal axis. Now when these light rays, forget this one, it will be more easier for you to understand. So these light rays, when they fall, they appear to diverge out. They appear to diverge out from the imaginary focus. So suppose how they now the imaginary focus is here and the light rays seem to diverge out from the imaginary focus and the image is formed at the focus, virtual focus. So position, focus, which is behind the mirror. Nature, now the image is behind the mirror, so it will be virtual and erect. And size, now it's highly diminished because as you can see here, this is this point. Now as we all know that we measure from the principal axis and it's just closely attached to the principal axis, so highly diminished. This is ray diagram 1. It appears to be reflected through the imaginary focus. Now let's see ray diagram 2 of convex mirrors. Here is ray diagram 2. Now the object is between infinity and the pole. So the light rays are coming and they appear to diverge from the virtual focus. Sorry for the disturbance. From the disturbance, virtual focus, they appear to pass. Now another light ray appears to pass through the imaginary center of curvature. So as we know, it retraces back. So the image is formed between pole and the focus. So now you can see the image, the size of the image is very small. So the now size is diminished. Not highly diminished, but diminished. Nature, virtual and erect. Now it's a very easy question if you have seen all my videos of this chapter. And position, behind the mirror, between P and F. Between P and F. So here this was the ray diagram 2 of convex mirrors. Now we'll see this in the PPT and then we'll learn about sign convention of mirrors and rays, which is basically similar. Now let's see the table which shows what we have learned. So this is for the image formation of the ray diagram by concave mirrors. This is the first ray diagram. The object is at infinity. The position of the image will be at F. Size of the image highly diminished. Nature, real and inverted. Come here. Position, second ray diagram, position of the object beyond C. Position of the image between F and C. Size of the image diminished and all nature of the image real and inverted. Now the object is at C. The image formation will be also at C. The size of the image is of same size and real and inverted. The position of the object is between C and F. Position of the image is beyond C. Size of the image is enlarged and the nature of the image is real and inverted. Again, the object is at F. The image is at infinity. The size of the image is highly enlarged while the image is real and inverted. And the last one between F and P, or the focus or pole, the image is formed behind the mirror, the size of the image is enlarged, and the nature of the image is here virtual and erect. So here are the all ray diagrams of concave mirror we have learned till now. You please take a screenshot. Now let's see image formation by convex mirrors. So here are the ray diagrams given below. Position of the object in the first ray diagram is at infinity. Position of image is at F behind the mirror. The size of the image is highly diminished, and the nature of the image is virtual and erect. And in the second ray diagram, the position of the object is between infinity and the pole. Position of the image is between pole and the focus behind the mirror. The size of the image diminished, and the nature of the image is virtual and erect. Now here are the uses of mirrors. As you can see here, concave mirrors are commonly used in torches, searchlights and vehicles' headlights to get powerful parallel beams of light. They are often used as saving mirrors because now in a saving mirror we need an enlarged image to see properly what is happening. Can see larger image of the face, dentists use a concave mirror to just see the large images of teeth of the patients. Large concave mirrors are used to concentrate sunlight to produce heat in solar furnaces. Convex mirrors are commonly used as rear view wing mirror in vesicles. Convex mirrors are preferred because they give an erect image through diminished image. They also have a wider field of view as they are curved. Thus, convex mirrors enable the driver to use a much larger area that would not be possible with a plane mirror. So here is an example of convex mirror and a concave mirror. You can see it gives in a concave mirror it gives a view of all the surroundings, while in a convex mirror it gives a highly enlarged image. Now let's see sign convention. What is sign convention? Sign convention is basically when we assign a place such as negative or positive to anything related to a mirror, such as components of a mirror and how the things or distance or the measurements of the mirror. Now why sign convention is important? Now sign convention helps us to see. Now suppose you are doing a numerical, we will learn about the rule of magnification. There are some rules, mirror formula, how it is, rules of magnification of a mirror after sign convention in this video only. So sign convention, it helps basically now you know that this is the height or this is the falana, this is the focal length. Now but how will you know that if the image is real or virtual, erect or inverted? Sign convention helps you with that. So here we learn about sign convention and how it helps us to understand or judge where the object is real, virtual and erect or inverted. So let's start. We'll do it with the rule of Cartesian plane. Now, you know what's a Cartesian plane? X and Y axis. So here is the origin and the pole. This is a concave mirror. And the pole is placed at the origin. Now here it's the positive y-axis, positive x-axis, negative y-axis and negative x-axis. Now in a concave mirror, what are the components of a mirror? See, center of curvature, pole, focus and the pole. Now if we have the height of the image of a concave mirror, the height of if we have the real image or the image here like this. So for the real image, if the answer is in negative, such as center of curvature is or a distance between the object and the pole, which is known as object distance, is negative or positive. So if it's negative, then it's a real image. Or CF of components of this mirror, curved inward mirror or concave mirror, are in negative value. Now the object's distance, which is object U, which is denoted by U, and small u, and the image distance from the pole, which is known as V. So now what happens in a real image? The image is formed downwards. So the height is towards the negative y-axis. The height is in negative, and the object, which is upward, is positive. And here the distance, incident rays, and here is the distance. This is the object distance, and this is the image distance. So this is sign convention using the Cartesian plane. The same case is for the convex mirror, which are coupled these words. And now the same C, Y, and this is towards positive. In a convex mirror, it's towards positive, and rest is the same. And the same for the lenses. Is that the object distance and the image distance is in negative, as it's in the front of the mirror. Convention, which we have already learned. In this convention, the pole P of the mirror is taken as the origin. The principal axis of the mirror is taken as x-axis of the coordinate system we have learnt. The object is placed to the left of the mirror, which amplifies the light of the object that falls on the mirror from the left-handed side. Now, basically, now no one will put the object behind the mirror, because then how will the light fall at the reflecting area? If you will put an image behind the mirror, how will you see that its reflection? All distances parallel to the principal axis are measured from the pole of the mirror. All distances measured to the right of the origin along x-axis are taken positive, while those measured to the left of the origin are taken as negative. Distances measured perpendicular to and above the principal axis along y-axis are taken as positive, while distance measured perpendicular to below the principal axis along y-axis are taken as negative. So here is the mirror formula and magnification. Now mirror formula needs anything on the board, so I'll explain you on the PPT only. You don't just have to see the mirror formula here. You can in our NCERT books there are many numericals related to this formula. So the mirror formula is basically the object distance, image distance plus the object distance. So as we learned about the focal length, image distance and object distance, so here is the combination or the similarities between these three. So here we see that the image distance plus the object distance is equals to the focal length. Distance of the object from its pole is called object distance U, and the distance of the image from the pole of its mirror is the image distance V, as we already learned. And distance from the principal focus from the pole is known as focal length. This we have already learned. Now magnification. Magnification, now if you have ever seen a magnifying glass, it helps us to see magnified image of the thing we want to see. Magnification produced by a spherical mirror gives the relative extent to the image of an object is magnified with respect to the object size. As the magnification rule is height of the image is by height of the object, or height of the image by height of the object is equal to minus V by U. This is the formula if you have the u and v, then you can get m, magnification. A negative sign in the value of the magnification indicates that the image is real, while now if the magnification value is in negative, then it's real. If it's positive, then it is virtual. Now let's see what next awaits us. Before moving on the video, please like, share, subscribe my channel, and also don't forget to click the bell icon segment below and share your comments in the comment section below. Now, as you all know, this video is part of Aryabhatta series, where I launch one video with high basic quality and good content per week, or 1 or 2 in 2 weeks. Thank you.